So today we are going to start on. Alright, yesterday when I talked about matching, that's not the final word. There's a lot more to matching. We are going to discuss matching in much greater detail over the course of the semester. But you can only go step by step. So first we are going to talk about the MOSFET. Now, you know the basic structure of a MOSFET. There's the, let's say I'm talking about an N-type MOSFET, then there is going to be a P substrate. I'm writing P negative, which basically means that lightly doped. Now, on top of this P doped substrate, we are first going to create an oxide. So we create the oxide. Hopefully this oxide has a uniform thickness all over the place. Later on, when we talk about matching, we will talk about how to avoid problems that are caused when the oxide thickness is not uniform, when there is a gradient. So we will talk about that later. So for now, let's assume that the oxide thickness is uniform. Then what happens?
Etching is done for the diffusion.
No, you first create the poly layer. First you create the gate, then you do the diffusion. So we first create the gate. How are you going to create a gate? You are going to create a mask for the polycrystalline doping, polysilicon doping, and then you are not doping, polysilicon layer, and then you are going to create a polysilicon layer. So that's going to give me a gate made up of polysilicon, which looks like that. And then you are going to remove the oxide. Now, where the oxide is shielded from the shielded by the polysilicon, you are not going to be able to remove the oxide. Otherwise, you remove the oxide. So basically, you remove this line, and it looks like this. Now you dope heavy N plus, as in heavy doping of N material, N-type material, phosphorus, all over the place. So once again, the polysilicon is going to shield the region beneath the gate. So you are going to shield it all over. You are going to dope all over the place. The polysilicon is going to automatically shield it from getting underneath the gate. So as a result, you will get something like this. Okay. Yes.
There will not be a ticket for the poly, and poly will behave as a field itself.
Yes.
But won't this doping affect the characteristics of the polysilicon itself?
This is how it's done. So all that is taken into account. It's taken into account. Okay. That the characteristics of the polysilicon will get altered, etc., etc. It's taken into account. In any case, you want the polysilicon to be conductive. So if you introduce N plus into it, fine. It's even better. Okay, so this is called the self-aligned process. Right? This is what we use all the time. Okay, now I'm going to call this the gate. Let's call this the source, the drain, and there isn't a terminal on the bottom side, but I'm going to call it the body. Typically, what happens is you create a P plus over here and connect the body over there. I'm not going to show all that. Okay? For now, for the ease of drawing, I'm just going to put the body terminal at the bottom. Alright. Now, suppose all of these terminals, source, drain and body, are connected together to 0. this is 0 volts. I'm going to ramp this from 0 volts all the way to 5 volts, and I want to know what happens when I slowly go from 0 volts to 5 volts. What's going to happen at 0 volts? Anything? Nothing. Okay. As you slowly increase the voltage on the gate, what is going to happen?
The electrons will be attracted.
Depletion will be formed. Why? Why? Why?
The electrons from the source of the metal will rush to the region below the gate.
No, I understand all that. I want to know why all this is going to happen at all.
Because the positive charge is being applied. So
Okay, why positive charge? Because you are connecting it to a positive voltage. So, if you connect the gate to a positive voltage, typically positive charge is going to show up over there. So, you are going to get some positive charge over here. Now, if you remember from your class 12 or class 11, the shape of a capacitor, the top plate and a bottom plate. If you have plus Q on the top plate, then on the bottom plate you need minus Q, right? Where is the bottom plate for this? I can see the top plate. The top plate is over there. Just below the oxide layer. The whole thing is the bottom plate. This whole region. Not the oxide. By mistake one line went over there. Not the oxide layer, but everything else is basically the bottom plate. So this entire region should accumulate a charge of minus Q. Okay? So first of all, our negative charge is there. Negative carriers there. Minority carriers, don't talk about minority carriers, please. Okay, I'll just give you a small calculation. You will see that there are no minority carriers. Let's say the size, the length of the gate is 0.1 micron, the width of the gate is 0.1 micron, the depth is 1 micron. I'm giving you easy numbers so that it's easy to calculate. So 0.1 micron is 1 into 10 power minus 7 meters. Let's deal with centimeters. Right? So 1 into 10 power minus 5 meters is the length. 1 into 10 power minus 5 is the width. I have to stop the screensaver from. Volume is equal to okay, and let's say that the amount of boron, when you dope with P minus, let's say the amount of boron that you have put in is how much? 10 power 16 per cubic centimeter. Okay. Then what is the value of N? Ten power 20 by 10 power 16 is 10 power 4. So how many electrons are there? Are there any electrons? No. There are no minority carriers anywhere. Let's be clear. Don't talk about minority carriers. Okay? So there are no electrons here. There are only holes. what's going to happen? The holes are going to move away. The holes are going to be repelled, basically. So the holes are going to move away from the gate, and in fact they are going to go into the ground terminal. Right? So they are going to sink out of the body, they are going to go into the ground terminal. As a result, what you are going to be left with are depletion charges, fixed charges, because the holes have left, the holes have gone away, so you are left with a net negative charge because the holes have gone away. These are not mobile carriers. These are because the holes have left the place. Holes are mobile carriers, they can move around. These things can't move around because the holes have gone. These are not really things. Okay, these are the absence of holes. Okay, so we are going to draw it, or rather people draw this in this fashion, minus with circles. Yes. N is the electron density, minority carrier density. This is the majority carrier density, this is the minority carrier density. N times P equal to 10 power 20, etc. At room temperature. You can see the whole thing. Okay. So the holes have left. Now, as you keep increasing this voltage at the gate, more and more holes leave. But there are only so many holes. How many holes are there in this? The volume is 1 into 10 power minus 14 per centimeter cube. This is the density of holes. So how many holes were there? 100 holes were there, approximately. So once the 100 holes leave, there isn't much more left, right? Then what's going to happen? If I still continue increasing the positive charge over here, now the inversion layer is going to form. Basically, electrons are going to rush in. Come on, this place has plenty of electrons. This place has plenty of electrons. So what's going to happen? Electrons are going to rush in from here and here, and they are going to create a channel. Now the electrons are mobile things, right? The absence of holes was not mobile, so the charge was spread out through the body. Now if I have some mobile carriers, where are the mobile carriers going to go? Mobile electrons. They are going to go up to the top surface because the positive is going to attract them to the top surface, right? So the channel is formed on the surface, right beneath the oxide, not in the bulk of the system, bulk of the MOSFET. Okay, so what all have I explained in the process? I have explained the depletion charge. I have kind of explained VT. Have I? Kind of explained. It's a very crude explanation, but that's more or less it. Okay? I mean, if you want to understand physically, when does the channel start appearing? That's a very good answer. Okay. So now you have the positive charge on the top, a negative channel, and charge in the bulk. This is called the depletion charge. It's a fixed charge because of the absence of holes. What's the relationship between these three charges? like a capacitor. If you have plus Q on the top plate, on the bottom plate it has to be minus Q. So the sum of that blue charge and the red charge, I've got to stop this screensaver from anyway. We'll do it next time. So the sum of the blue colored material and the red colored charge is equal to the black colored positive charge. Right? This is understood. Okay. Now what happens when I create a channel? What have I got? I have developed a connection between source and drain. Okay? Now, if I want things to move between source and drain, they can move. Things as in electrons. Okay, I now have a straight conducting path between the source and the drain. Before the channel was formed, there was no path between the drain and the source. Right? Electrons in the drain were not talking to the electrons in the source. Now, there is a straight path through which current can probably go if I want it to go. So now if I make the drain 1 volt, what's going to happen? Yes? I will get current in which direction? From the drain to the source. What happens if I make the source also 1 volt? Both the source and the drain 1 volt? No current is present. What happens if the source is 1 volt, drain is 0 volts? Current will go in the other direction. Right? This is very clear. Current really means opposite of the flow of electrons. If current goes in one direction, electrons are going to go in the other direction. So really, what's going to happen is, when the drain is at 1 volt, electrons are going to be attracted to the drain. So right now I have drawn a uniform layer of the channel. Okay, uniform charge density in the channel. When the drain becomes 1 volt, this is not going to be uniform anymore. There are going to be more electrons on the source side and less electrons on the drain side. Now, the way I've drawn it, it looks like the channel is going into the depth of the system, into the depth of the body. No. This really indicates the electron density. So the electron density is higher at the source, lower at the drain. All the electrons are at the surface and only the surface. Okay, they are not at any other place. The old equation for the old relationship between the three charges, the black charge, the blue charge and the red charge, still holds. Okay, the blue charges are all attracted to the surface. They are all sitting on the surface only. I am not going into the depth that I have drawn it. This is just an indication of the density of the electrons. So far so good? Is this okay? Now there is one thing that I have not yet talked about, and that is the fact that the source is an N plus material, the body is P minus material. The drain is N plus material, the body is P minus material. These two form PN junctions. Okay? Now if the source is at 0 volts, body is at 0 volt, what's going to happen between the PN junction of the source and the body? There will be a built-in potential, I agree. A built-in depletion layer. Fantastic. Why is this depletion layer happening? So there are some free electrons on the N plus side and there are some free holes on the P minus side. They combine with each other. So it's called recombination or whatever. Right? So they combine with each other, and in that pink zone, it's blank. There are no mobile carriers there. Okay? When I say there are no mobile carriers, really what it also means is that there are some fixed charges there. Aside. Similarly, there is going to be another depletion region between the drain and the body. Now, is that depletion region going to be larger than this one or smaller? Why is it going to be larger? Drain to body junction is reverse biased, so the depletion width will be more in that case. Oh, again screensaver has started. Now, as I have drawn it over here, it looks as if this depletion region is interfering with the channel. Does it really interfere with the channel?
Yes, sir, it does.
Let's talk about the source region.
So the source region, that electrons will flow from n minus to p plus only after negating the impact of this depletion region when the sufficient carriers will flow from the other side to.
Is it significant? Is this depletion region significant? First of all, you have to understand that the way I have drawn it is not right. The electrons are going to be at the surface. That's number one. Number two, this thing is already depleted of all the holes. Okay? Beneath the channel, there are no holes already because of other reasons. So over here, there's not going to be really much recombination going on because there are no holes to start with. Okay? So that's really not of concern. It's really an artifact of the way I have drawn it. Right? So first of all, the charges move out. So there is nothing to recombine with over there. Underneath the channel, the holes are already gone because of other reasons. Agreed? Okay. So we have understood a few things. First of all, as you increase the gate voltage, the density of electrons in the channel becomes more and more. Why?
No. More the potential gradient, the more electrons will flow from.
No. Think about that relationship between the three charges. If I increase the black charge, then the blue charge has to increase because the red charge can't increase, really. Okay, there are only so many holes. There are 100 holes in this. Holes have gone out. Then the blue charges start up. So as I increase black charges, blue charges have got to increase. When I increase blue charges, the density of the electrons on the surface increases. Okay? So as I increase the gate voltage, I get a stronger and stronger connection between the drain and the source. Okay. Now, what does that translate to as far as the current is concerned? If I apply a drain source potential of 1 volt, as I have applied, then what does that mean? If I increase the gate voltage, what happens to the current? The current is also going to go up because now the channel can conduct more current because the channel has lot more electrons handling. Okay? Okay. So going to call this Vg. Yes. Charge and charge density. Yes. Both. Yes. Not on source to drain. The amount of charge only depends on the gate voltage. As I increase the gate voltage, the amount of charge in the channel increases. Yes. Okay. The profile changes. The density profile changes because of the source to drain voltage, nothing else. Okay, my charge balance equation, plus Q on one side, minus Q on the other side is true. Has to be, that charge balance has to be taken care of. So I'm going to write this as Vg. Yes.
What happens if the electrons are also out? Typically, you get a previous number. Suppose if the electron density in the source region is, let's say, it is 10 more degrees now, and the area is 10% of the total volume.
You mean volume? Volume is
10% of the total volume. Typically, number of electrons in source and drain.
you'll have to increase the doping to make it work.
So what happens if the
It won't work. That's why there is so much process engineering, etc., as we go into smaller and smaller geometries. Right? As we go forward, you have to engineer all these numbers.
in other words, say if I increase the voltage beyond the plus Q far larger than the number of electrons and the deflection, the negative charge. Now I am looking at it in a different way. Increase the voltage.
Okay, if you increase the gate voltage so much that there aren't that many electrons in the source and the drain at all. Over time, you have to understand they are going to come from this supply. Okay, also they are going to come from this supply. Over time. Okay, the source is 0 volts already. Okay, it's a slower process. If it comes through this, then it's a very slow process. It takes a lot of time. If it comes from here also, it's slower than what is readily available. Okay? What is more worrisome in this case, when you keep increasing the gate voltage, is that lightning will strike across the oxide. Okay? And the device will become useless. Because when you exceed a certain amount of electric field density, right? When you exceed a certain amount of electric field density, then lightning will strike from the gate to the channel. Once lightning strikes, the oxide is ruptured and basically it melts because a lot of heat is generated. Okay? So that is something which is of more concern. What we typically do is, those who design these processes, etc., make sure that all this is taken care of and the device works at full speed. All these numbers are crunched out and they design the device properly so that things work. There are enough number of holes and electrons all over the place. Okay? Minority carriers are not there. Sorry, no minority carriers. But majority carriers are there. Now, so far I have not done any equations. Really, I I mean, the only relationship I talked about was the fact that the positive charge is equal to the negative charge. That's the only relationship. But right now I'm going to draw some curves. Take this on face value, okay? Or if you've done a MOS course, then take this based on that course. So what happens is, if I plot if I plot IDS, the current going from the drain to source, as a function of VG. Why I'm writing it as VG and not VGS is because I'm already assuming that S is connected to B, which is connected to ground. Okay. So this typically looks like this. There's some sort of square law, may or may not be. It looks like this. Don't ask me what the shape of this curve is. Okay, modern devices, it's no longer a square relation. You will get some kind of a threshold voltage over here, after which things will really start rolling. Actually, this is not the definition of VT. VT is defined as this point. Some asymptote you draw and where it intersects. Anyway, it really doesn't matter where all these numbers are. It matters if you are doing a course on modeling the MOSFET, etc., but not for us. What you have to understand is that beyond VT, there is the density of charge in the channel is very high. Okay? Below VT, from my crude explanation, it sounds like there is no channel. Not really. There is a small amount of channel charge. Okay? So below VT, there is still a small amount of channel charge. Beyond VT, there is a large amount of channel charge. This is something I need you to understand. So we classify the operation of the MOSFET in 3 regions. So strong inversion, moderate inversion and weak inversion. Moderate inversion is when the gate to source voltage is approximately equal to the threshold voltage of the device. Weak inversion is when the gate to source voltage is less than, let's say, VT minus 6 kT over Q. And strong inversion is when VGS is greater than VT plus 6 kT over Q. Okay, 6 kT over Q is something like 150 millivolts at room temperature. So we classify the operation of the MOSFET in these 3 areas: strong, weak and moderate inversion. Moderate inversion is between these 2. Okay, so VGS is less than VT plus 6 kT over Q, more than VT minus 6 kT over Q. So probably you can say that this is weak, this is moderate, and the rest is strong. Okay, the curve doesn't go on forever because soon lightning strikes across the junction and you throw away the device. Older textbooks will say that this curve is a quadratic. That's square law to it, etc., etc. Now, modern processes, modern MOSFETs, this curve is no longer quadratic, it's somewhat linear. Really doesn't matter how this curve looks. Okay? For this course, if you are concerned about the exams, etc., I will give you the relationship at the exam. So, whatever this curve follows, whatever mathematical relationship this follows, I will give it to you in the exam. Okay, books. Older books will say that ID is something like this. Okay, this particular curve works in this fashion. Okay, this is what older books will say. I will give you whatever relationship I want you to use at the exam. I will give it to you at the exam. Okay, it's not of much concern what this relationship is. Modern processes, this is not the relationship anymore. It's more or less linear. Okay. Now, this is when I plot ID as a function of the gate voltage, or rather the gate to source voltage. I can also plot ID ID is really equal to, the drain current is equal to the source current. Why? Yes, but from a circuit theory point of view, why? No gate current. Why is there no gate current? There is a layer of glass in between, so it's a very good insulator. So, for this class, we are going to assume that there is no gate current. Now, here I am going to point out that modern transistors, modern MOSFETs, the gate is so thin, that layer of insulation material is so thin, this layer of glass is so thin, it's a few atoms thick. Okay, and when we talk about a layer which is a few atoms thick, few as in 5, 6, not even tens of atoms. When we talk about that thin a layer, then there is tunneling current from the gate into the channel. Okay, quantum mechanics comes into play, and strange things happen. Cat is in the bag, cat is out of the bag, etc. So, there is a small gate current in modern MOSFETs. So, tomorrow if you go to a company and you tell them that, look, the gate current is not there, it's 0, they will laugh at you. Okay, so gate current is there when we talk about modern devices. However, it's small. It's a fraction, it's a small fraction of the drain source current. So, small fraction may be something like 1/100th or 1/50th. Okay, so 1% or 2% of the current that's going from the drain source. Alright? What about the body current? Is there a current into the body? There are 4 terminals here, right? Gate, source, drain and body. Is there a current into the body? Yes? Why? Reverse leakage of the junctions. Okay. Which is very, very, very small, considering the fact that there are no holes in the P minus at all. Okay? No minority carriers this current is more probabilistic than anything. Okay, there's a small probability that there is going to be a current. So if there are 1 million devices that you are talking about, then one of the 1 million devices will be, let's say the probability is 1 in a million, right? The probability to find a hole in spite of all this is so the hole density or minority carrier density you computed it to be so much. Okay, it's not 0, but it's much less than 1, which means that there is a small probability that you will find a minority carrier over there, which means that if you have a million devices, then some of those will have a few, so that will give you small amount of reverse bias current, reverse leakage current. Okay, nothing else. If you're talking about a single device, there's nothing, no reverse leakage. Alright, so given these considerations that reverse leakage current is not of concern and that the gate current is a small fraction, maybe 1/100th or 1/50th of the drain and source currents, we are safely going to assume that the drain current is equal to the source current. Kirchhoff's law. Okay? Okay, body current is 0, gate current is tiny. So we are safely going to assume that drain current is equal to source current. So IDS is basically the same as ID, which is the same as IS. Alright? So typically how this looks is something like this, and all of these multiple curves are at multiple values of VGS. So as I change VGS, as I make VGS larger and larger, these strange things happen. Now it's intuitive why it's increasing. Let's analyze one particular curve. Okay. It's intuitive. First of all, it's intuitive that between this curve and this curve, why there is an increase in current. That's intuitive, right? Because the density of electrons in the channel has increased, so the current will naturally be more. There is more gate charge. Okay, so that we understand. We also probably intuitively you will be able to understand the initial increase. Why it increases? Why does it increase? As you increase the potential difference between drain and source, it's Ohm's law, right? You increase the potential difference between drain and source, more current will flow. Then what happens? That doesn't seem to be intuitive at all. What's going on?
So at a particular gate voltage, the number of
Gate or drain? Drain to source.
So when there is a particular gate voltage, the density of charge which is in the channel then remains constant. So when we increase the drain to source voltage, since the number of the carriers is constant, so a particular amount of current depending on the carrier density will flow, not more than that. So the current saturates in that condition.
Okay, so given the fact that there are only so many electrons in the channel, what's your name? Charu is saying that given the fact that there are only so many electrons, n number of electrons in the channel, there is only so much current that can flow, not more than that. Do you agree? What happens in a resistor? Why can infinite amount of current flow? I mean, Ohm's law looks like this. If I take a 1 kilo ohm resistor, I keep increasing the voltage across, the current keeps increasing. Why? What's the difference? Charge comes from the battery is fine. What else? Number of collisions increase here also. That's what he's saying, right? There are only so many electrons. So once the drain attracts so many, then it gets pinched off. There are only so many electrons. That's fine, that's pinch off. But why doesn't pinch off happen over there?
So bulk
device.
So the value of the conductor, so there are
Thank you. So a resistor is made out of a conducting material. What does a conducting material mean? There is an ocean of electrons. Okay? You have infinite number of electrons available. They are all freely moving here and there. There are so many electrons that you are never going to use up all of them. Okay? The material is not conducting. The material is semiconducting. There are a finite number of electrons. Okay, that's really the explanation. Now, you would think that how can it really be an ocean of electrons? I mean, there are so many atoms, so there have to be so many electrons. There can't be more than so many. Really, by that time we will burn the resistor. By the time you reach that limit, the resistor will burn because of other reasons. Okay? Fine. So we kind of understand why this flattens out. Now what does this hint at? From usage perspective, if I were to use the device as something, what would I use it as?
voltage.
A voltage controlled current source. A current source, basically, right? I am increasing the voltage on this axis and the current is not really increasing. That's the action of a current source. Or rather a voltage controlled current source, because I can control the amount of current that I want to conduct. As opposed to a resistor where the current keeps going up. Okay? I think it's time. Okay, so we are going to follow on the lines of this, that the MOSFET is really a voltage controlled current source, number one. For analog circuits, it's a voltage controlled current source, and for digital circuits, it's a voltage controlled switch. I mean, channel is present, channel is not present. If I apply a voltage, channel is present, the switch, the connection between drain and source is on. There is a connection. If I don't apply that voltage, there is no connection between drain and source. Right? So these are the two ways to use a MOSFET. Okay, thank you.